Welcome to the Deep Dive. Today, we're digging into a really big challenge for large language models.
Yeah.
How do you handle these super long sequences, lots and lots of text, without the compute costs just going through the roof?
Exactly. And we're basing this discussion on a really important new paper. It's called The Sparse Frontier, Sparse Attention Trade-offs in Transformer LLMs.
Right. And our mission here is really for you, if you're, say, an AI researcher working on model designs, or maybe an ML engineer trying to actually deploy these things for long context tasks. We want to unpack this paper for you, give you the key takeaways on, viability, efficiency, accuracy trade-offs when you use sparse attention, getting right to the core of making attention scale. Okay, so let's do a quick upfront summary. If you only have a minute, here are the absolute highlights from the paper. Finding number 1.
Yeah, the first big one is this IsoFLOPS analysis. It shows that for really long sequences, we're talking like 128,000 tokens, sometimes a larger model that's made highly sparse can actually be better, more efficient than a smaller, dense model using the same amount of computation.
Wow, okay. So that kind of flips the usual scaling idea on its head.
It really does. Finding 2. You can generally get away with much higher sparsity levels, skipping more calculations, especially during decoding generating token by token. And bigger models handle this better. But, and this is really crucial, even moderate sparsity can cause performance to just tank on some specific tasks. So it's definitely not a universal fix.
Okay, not a silver bullet, which leads to finding 3, I guess.
Precisely. There's no single best sparse attention method that wins everywhere. What works best really depends on the task. Is it retrieving specific facts, or is it more about reasoning across the whole text? And it also depends on when you apply it during the initial prompt processing, the pre-filling, or during the token generation, the decoding.
Makes sense. Different needs for different situations. And the last one? Finding 4.
Finding 4 is about predictability. They actually developed scaling laws for sparse attention. This suggests the patterns they saw in their experiments are pretty robust and likely generalize. You might be able to predict performance trade-offs without running every single test case.
Okay, super useful.
So yeah, the big picture is sparse attention is critical for long context, absolutely. But you need to be really careful and evaluate it for your specific use case. Average performance can hide some nasty surprises.
Right. Let's back up a bit then. Why is this even a problem? What's the bottleneck with standard dense attention in transformers that makes long contexts so hard?
Well, the fundamental issue is the self-attention mechanism itself, right? For every single token, it looks at every other token to figure out relevance.
The n-squared thing.
Exactly, the quadratic cost.
Yeah.
If you have n tokens, you're doing roughly n-squared calculations. So during pre-filling, when the model first reads that long prompt, this n-squared computation directly impacts how long it takes to get that very first output token. And, the overall cost just blows up as n gets bigger.
Okay, that's pre-filling. But what about decoding? When it's generating the answer one token at a time. That's not n-squared every single step, is it?
No, it's linear OM per step then, because you've got one new token looking back at all this and previous ones, but the bottleneck just shifts. It's less about the raw computation per step and more about memory, specifically accessing the key value cache, or KV cache.
Ah, right, where it stores the representations of all the previous tokens.
Exactly. And as you generate more tokens, that cache gets bigger and bigger. Moving data back and forth from this potentially huge cache becomes the main thing slowing down runtime during decoding.
Got it. So quadratic compute hell for prefill, memory bandwidth hell for decoding, and sparse attention is meant to help with both by, just doing less work.
Pretty much, yeah. It tries to approximate the result of full dense attention, but by only calculating a subset of those query key interactions.
Skipping some connections.
Right. So for pre-filling, that directly cuts down the n-squared computation. And for decoding, because you only need some of the keys and values, you reduce how much data you need to pull from that big KV cache, easing the memory bottleneck.
Okay. And the paper talks about sparsity and compression ratio. Sparsity is just the fraction you skip, right? Like 0.9 means you skip 90%.
Correct. And the compression ratio is just a different way to look at it. 1 divided by 1 minus the sparsity. So 0.9 sparsity gives you a 10x compression ratio.
Meaning you're trying to do the job with roughly 1/10 the attention work.
That's the goal, yeah. Get similar quality with much less cost.
Okay, so how do you actually choose which interactions to skip? It can't be random, surely. The paper lays out this framework, right? 4 dimensions to categorize these training-free methods. What's the first one?
The first dimension is the unit of sparsification. Basically, What are the chunks of the attention matrix you're working with? Are you deciding to keep or drop individual token-to-token connections? Or are you working with bigger pieces?
Like deciding word by word versus, I don't know, paragraph by paragraph.
Sort of, yeah. It could be small things like specific query key pairs, or larger units like fixed size blocks, say 64 tokens by 64 tokens, or maybe local windows only looking at tokens nearby, or even entire columns, letting one query see everything.
Okay. And there's a trade-off there.
Definitely. Bigger units like blocks or windows tend to be more hardware friendly. You can compute them faster. But smaller units give you finer control, letting you be more precise about which specific, maybe crucial connections you keep. It's efficiency versus precision.
Got it. So you decide the size of the chunk you're keeping or dropping. What's dimension 2? Importance estimation.
Right. So you've got your units. Now, how do you figure out which ones are actually important enough to keep? The paper focuses on content-aware methods. These look at the actual text, the input, to decide, rather than using a fixed pattern like, say, always looking at the previous 10 tokens.
That sounds much smarter for our language. How do they estimate importance? Do they run a mini attention first or something?
Not quite full attention. That would defeat the purpose. They use heuristics, kind of like quick approximations. They might look at how similar token representations are or use simplified attention score estimates. The idea is to get a quick signal about which units are likely to be relevant, then keep the top K based on whatever budget your sparsity target gives you.
Like skimming before reading closely.
Exactly. Different methods use different tricks, maybe focusing on recent tokens or aggregating scores somehow. These methods add a little overhead for the estimation step, but the paper shows they generally perform much better than fixed patterns, because fixed patterns can easily miss important but distant context.
Makes sense. You need to know what to keep. Okay, dimension 3, budget allocation.
Yeah. So you have a total budget. Let's say you want 10x compression overall. How do you spread that budget across all the different attention heads and layers in the model?
Do you just give everyone the same tiny slice?
That's the simplest way, uniform allocation. But as you know, different heads and layers often specialize in different things. Some might track syntax, others might find facts, others might handle long-range stuff.
Right, so uniform might starve a critical head.
Potentially. So adaptive methods try to be smarter. They might allocate more budget to heads or layers that seem more active or important for the current input or task. Some even adjust the budget dynamically, maybe relaxing the sparsity slightly if they aren't capturing enough attention mass, enough important connections based on some threshold.
Interesting. Okay, so granularity, deciding importance, distributing the budget. What's the fourth dimension?
The fourth is KV cache management. This is really about the decoding phase and that memory bottleneck we talked about. Once your sparsity method decides certain keys and values are less important right now, what do you actually do with them in the cache?
Do you just delete them? Free up the memory?
That's one approach, called eviction. Methods like SnapKV do this. They physically remove the less important tokens or blocks from the KV cache. The huge benefit is you genuinely reduce the memory usage and the data transfer costs. The big risk: what if that token you threw away becomes critical later in the generation? That information is just gone. It's a permanent decision.
Ouch. Yeah, that sounds risky. What's the alternative?
The alternative is to keep the full KV cache stored somewhere, but get smarter about accessing it. Methods like Quest do this. They might use extra data structures like indexes to quickly find and selectively load only the KV pairs identified as important for the current step.
Ah, so you keep everything, preserving all the information, but you try to only touch the bits you need right now.
Exactly. The upside is no information loss. The model can always potentially look back at any token. The downside is you don't actually reduce the peak memory needed to hold that potentially enormous full cache. You're optimizing the transfer, not the storage footprint.
Okay, that framework unit, importance, budget, cache management, really helps break down the different strategies. Now, the paper tested these ideas pretty extensively, right? Using the Quinn models.
Yeah, a massive empirical study. They used the Quinn 2.5 family, models from 7 billion all the way up to 72 billion parameters. A key reason was these models support a huge 128,000 token context window natively, and they have a consistent architecture across sizes.
And they pushed the sequence lengths right up to 128K and tested sparsity going up to 95%. That's 20x compression.
They did, really pushing the boundaries. They picked 6 specific content-aware sparse methods that represented different points in that 4-dimensional space we just discussed. Things like vertical slash, block sparse, SnapKV, Quest, a good mix.
And they didn't just test on one type of task, right? They used a whole suite.
Crucially, yes. 9 different long context tasks, because, as we suspected, performance varies a lot. They even categorize the tasks based on characteristics like dispersion, how spread out is the info you need, and scope, how much of the text you need to process.
Like the difference between finding one specific number versus summarizing the whole document.
Exactly. They use standard benchmarks like squad and quality, but also synthetic tasks from the ruler benchmark designed to stress specific abilities, needle in a haystack for retrieval, multi-hop reasoning, aggregation. And they even created new story tasks based on narrative text to mirror those challenges in more natural language.
Okay, quite a rigorous setup. So let's get back to the key findings. That first one, the IsoFLOPS analysis comparing small, dense models to large, sparse ones.
Right. Research question 1. They plotted performance against the computational cost, FLOPS, for different model sizes and sparsity levels, looking at the average across tasks. For shorter sequences, like 32,000 tokens, the picture was kind of mixed. Smaller, denser models were often right there on the efficient frontier. Making models denser was a reasonable way to trade compute for accuracy. The non-attention parts of the model were still a big factor.
But then at 128,000 tokens, the picture changed dramatically.
Completely shifted. At that very long sequence length, the cost of dense attention becomes so overwhelming that those smaller, dense models just aren't efficient anymore. The only models sitting on that Pareto frontier, the best trade-off points, were the larger models made highly sparse.
So that's the efficiency crossover they talk about.
Precisely. It's the point where adding parameters and adding sparsity becomes more computationally efficient for achieving high performance than just using a smaller, denser model.
Okay, so for really long inputs, the path forward seems to be bigger and sparser, not just denser.
That's what the analysis strongly suggests. And there's a related point. The larger models, like the 32B and 72B parameter ones, were much better at tolerating high levels of sparsity without performance drops, especially during decoding using the Quest method compared to the smaller 7B model. So size helps sparsity work better.
Fascinating. Okay, finding 2 was about just how sparse you can get away with. What did they find on average?
This was RQ2, using statistical tests to find the maximum compression before performance was significantly worse than dense. On average, for pre-filling with a method called vertical slash, they could tolerate over 10x compression. For decoding with Quest, it was even more impressive, especially for the bigger models. The 32B and 72B models averaged around 17x compression tolerance, and on many tasks, they could hit the maximum tested 20x compression without a significant drop.
Wow, 17x or 20x average tolerance sounds incredible. But you mentioned a huge caveat earlier.
Yes, and this is absolutely critical for anyone thinking of deploying this. Despite those really high average tolerance levels, when they looked task by task, they found that almost every single configuration, model size, method, sequence length failed badly on at least one of the 9 tasks, even at quite moderate compression levels, like below 5x.
Wait, say that again? Even at less than 5x compression, skipping less than 80%, most setups failed on some tasks.
That's right. The only exception was the largest model, 72B, using Quest for decoding. Its worst-case failure point across all tasks was still at 10x compression. But for everything else, there was at least one task that broke much earlier.
So your model might seem fine on average at 10x or 15x compression, but for certain inputs or queries, it could just completely fall apart, even if you only use 3x or 4x compression.
Exactly. It highlights the danger of relying on averages. Sparse attention isn't just a knob you turn down uniformly. It can selectively break things in ways that average performance metrics totally hide. You have to test on tasks representative of your actual use case.
That really changes the game. You can't just assume moderate sparsity is safe, which flows right into finding 3. Different methods work better for different tasks. Can you elaborate on that?
Yeah, RQ3 dug into this task specificity, figure 4 in the paper. Let's think about retrieval tasks first, finding specific, often scattered pieces of info. Think needle in a haystack. For these, performance tended to drop pretty steadily as compression increased, especially if you needed to find multiple needles in the same haystack.
Why is that?
Well, methods that select important tokens globally, like vertical slash or snap KV, struggle because when you need lots of specific unrelated tokens, a limited global budget makes it hard to capture all of them. And methods that work with blocks of text, like block sparse prefilling, are inefficient because the needles might be in different blocks, and selecting contiguous blocks isn't helpful.
So block-based is bad for finding scattered things.
Generally, yes, unless the method is flexible. Quest, which uses chunks but selectively loads them per query during decoding, was a standout. It managed near-dense performance on their natural language story retrieval task, even at 20x compression. That shows the power of fine-grained query-aware access during generation. Though, interestingly, Quest didn't do as well on the synthetic ruler NIAH retrieval task, hinting that how information is distributed in synthetic versus natural text matters.
Okay, so that's retrieval. What about tasks that need a broader view, like aggregation or multi-hop reasoning? High scope or dispersion tasks?
Here, the picture often flipped. Chunk-level methods like BlockSparse for prefilling and Quest for decoding frequently did as well as, or even better than, the token-level global selection methods.
Why would BlockSparse, which struggled with retrieval, do well here?
Because the structure of some of these tasks, like ruler VT, multi-hop, or their story filtering task, might involve processing information that's more localized within chunks or chapters. BlockSparse's approach aligns better with that kind of processing, and Quest really shone during decoding on complex aggregation, ruler CWE, and multi-hop tasks. Why? Because it keeps the full KV cache. It doesn't throw information away like eviction methods, snap KV. This means the model can always trace back complex reasoning paths or aggregate information from anywhere in the context, which is vital for those harder tasks.
That makes perfect sense. If you might need anything, you can't afford to delete parts of the context. What about the budget allocation dimension uniform versus adaptive?
That showed interesting phase differences too. During prefilling, the adaptive method they tested, flex prefill, was surprisingly tricky. It sometimes did worse than simple uniform allocation, vertical slash. It seemed sensitive to settings and could sometimes miss widely distributed information, maybe related to that attention sink idea, where some tokens just attract attention regardless of relevance. But during decoding, adaptive allocation, Ada snap KV, consistently beat its uniform counterpart, snap KV, especially on those tricky multi-query tasks. This suggests that while simplicity might be robust upfront, dynamically adjusting attention across heads during generation is actually beneficial.
Okay, so wrapping up RQ3, the message is loud and clear. There's no single winner.
Absolutely not. You need to think, am I optimizing prefill or decoding? Is my main task retrieval, or is it reasoning or aggregation? Based on that, you choose a different combination of sparsity unit, importance estimation, budget allocation, and KV cache strategy. Flexibility often helps, but methods like Quest have their own costs, like needing extra memory for its index.
All right. And the final key finding, number 4, was about scaling loss. Could they actually predict this complex behavior?
That was RQ4. They tried fitting a relatively simple log linear model to predict task performance based on things like model size, N, sequence length, L, compression ratio, C, and the specific task itself.
And did it work?
Surprisingly well, actually. The models had high R-squared values, meaning they explained a good chunk of the variance in performance. And the coefficients made sense. Performance generally went down with longer sequences and higher compression, and up with bigger models. The task-specific parts reflected known difficulties.
The crucial test, though, could it predict performance in situations it hadn't seen during training, like predicting for the 128K length having only seen up to 64K?
Yes, they did hold out tests like that, evaluating extrapolation. And generally, the predictions held up pretty well. The correlation between predicted and actual scores remained strong, and the prediction errors were mostly reasonable.
So these trends seem robust.
It suggests so, yes. That the relationships they observe between size, length, compression, task, and performance are likely to generalize. It gives us a tool, potentially, to estimate these trade-offs without having to run every single costly experiment.
That's incredibly valuable. Of course, they probably noted it wasn't perfect everywhere.
Oh, for sure. They pointed out specific settings where prediction was weaker. Modeling these complex interactions perfectly is still a huge challenge. But overall, the fact that these scaling laws showed robustness is a significant finding.
Definitely. Okay, this has been a really insightful dive into the sparse frontier. Let's try to wrap it up for everyone listening. What are the absolute key things to take away from this paper?
1. Sparse attention isn't optional anymore if you want to scale to truly long context. It's essential. 2. The scaling strategy might flip. For very long sequences, think bigger models with high sparsity, not just smaller, denser ones. 3. High average sparsity tolerance, especially for large models in decoding, is achievable, and it's a huge, but task-specific failure is a major risk. Moderate sparsity can break things unexpectedly. Averages lie.
Right. Don't get complacent with average performance. And 4.
4. Method choice matters a lot. It depends heavily on the task retrieval, reasoning, aggregation, and the phase prefill versus decoding. There's no one-size-fits-all sparse method.
And finally, these complex trade-offs seem to follow predictable scaling laws, which is encouraging for future work.
Exactly. These findings really cement sparse attention's role in future LLMs, enabling more scalable, efficient models. But deploying them successfully, that requires really careful, application-specific thought and testing.
Which leads to a final thought for you, the listener. Given these task-specific pitfalls, where even moderate sparsity can cause failures, how do we move forward? How can we design sparse attention systems that are truly dynamic, that adapt reliably to any input or task, maybe even offering some kind of performance guarantee instead of just good, average behavior? That seems like the next frontier.
A critical challenge indeed. Lots to think about there.
Well, that brings us to the end of this deep dive on the sparse frontier. We really hope this discussion has helped clarify the complex world of sparse attention for long context models.
You can and should check out the full paper for all the details. And the authors have made their code available on GitHub too, which is great. The link's in the paper.
Definitely worth exploring if you're working in this space. Think about how these trade-offs and pitfalls might affect your own projects. Thanks so much for joining us for this deep dive.